Okay, so today we'll be looking at criteria, or one really only criterion for when a given graph is planar. Informally we say when it can be drawn in the plane. Officially that means when it's isomorphic to a plane graph. And this isomorphism is then called an embedding. So there are some such theorems that tell you when a given graph is planar, and there are even some quite exciting theorems about this. They're a bit more algebraic than we can do in this introductory course, so they'll be in graph theory too, unfortunately. But there's something really nice going on there, which you wouldn't normally suspect, because planarity by definition is a sort of pedestrian kind of thing, at least from a combinatorial point of view. But there are very nice algebraic embedding or planarity criteria to be met in graph theory too. So now, today, we'll look at the best used and most applied planarity criterion that there is, and that's Kuratowski's theorem. So what's that? 4, 4, 6. As early as 1930. So Kuratowski was a topologist, really, even though topology was only being invented at the time properly. Some aspect of it, which I'm going to point out in a moment, were proved a little later by Wagner. So Wagner is one of the two sort of fathers of graph theory in Germany. He was in Cologne, Klaus Wagner. His students were Harlin, Madder, and Jung. And what does it say? It says that a graph, finite graph as always, is planar if and only if G has neither a particular graph K5 nor another particular graph K33 as a minor. And this is, in fact, Wagner's version of the theorem, and Kuratowski's original version was that G doesn't contain these as a topological minor. So G doesn't have a subgraph that's a TK5 or a TK33. And this is G doesn't have a subgraph that's an IK5 or IK33. Right, so that's Kuratowski's theorem. To give you a little bit of background, if we think of sort of out of the blue, how can we possibly try to characterize planarity, then one early observation is that the class of planar graphs, so these are all graphs. This is my universe of graphs. Universes are always drawn like that. So these are the planar graphs, and I'm drawing them nicely at the bottom because when you look at the minor relation, or indeed the topological minor relation, the class of planar graphs is closed down. If you have a planar graph and you take a minor, then that's, again, going to be planar. You can see that topologically, right? If you delete something, you can do that in a plane graph, and it'll remain a plane graph. And if you contract an edge, you can also do that in a plane graph sort of You have to fiddle a little bit, but it's easy, right? So the planar graphs are closed under the minor relation, and whenever you have a graph property that is closed under some relation, I mean some partial ordering, such as minors or subgraphs or induced subgraphs or whatever, you can characterize that property by excluding the minimal graphs without that property. So a graph is planar if and only if it does not contain one of these graphs as a minor. And what are these graphs? They're the minor, minimal, non-planar graphs. Right? And that's clear, because if a graph is planar, it can't contain a non-planar graph, any of those, as a minor, because planarity is closed under taking minors. So any minor of a planar graph is, again, planar and not up here. So if a graph is planar, it doesn't contain one of those. And if it's not planar, it's somewhere up here. And then you make it smaller, 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 remaining non-planar, any old how. And then you'll arrive necessarily at a minimal graph that is non-planar. That's one of those, by definition. This is defined as the set of, or the class of, minor, minimal, non-planar graphs. Okay. Incidentally, this uses finiteness, right? So in infinite graphs, you could take minus, 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 and never get anywhere. Right? You get smaller and smaller and smaller. Quite exciting. So there's also something exciting about finite graphs even, and that is it's not clear a priori that this class of minor minimal graphs that are not planar is even finite. Right? There are arbitrarily large non-planar graphs. And you could get to a minimal one here, and get to a minimal there, get to a minimal one there, and so on. So why should the collection of minimal graphs that are non-planar be finite? It's not clear, and it's the deepest theorem in finite graph theory, or in graph theory, that for every minor closed class of graphs, the class of minimal graphs not in that class is finite. That's the graph minor theorem by Robertson and Seymour. We get to that, unfortunately, also in graph theory too, but there's a lot of stuff going on there, so that's really quite exciting. Anyway, so Kuratowski's theorem is the prototype of such characterizations of minor closed graph properties. And it says that there are only two graph minor minimal ones, K5 and K33. Right? So that's Kuratowski's theorem. Okay, questions about that? Sort of about the general nonsense and stuff? Okay. Right. So let's see. For a proof that K5 and K33 are not planar. Let's prove that first. And once we've shown that, then it's clear that subdivisions of K5 and K33 cannot be planar either. Right? So if you... so why are they not planar? Basically, they have too many edges for their number of vertices given Euler's formula. Right, Euler's formula says that n minus m plus f is 2. And so given n, if you make m too big, then that deviates from 2 too much. And that's sort of very, very roughly the idea, and let's make that more precise. So we looked at plane triangulations and proved that they had exactly 3 n minus 6 edges. I'm going to show you that K5 and K3 have too many edges. So I'm going to show you that K5 has more than 3 n minus 6 edges. Right, 3 n minus 5. So 3n is 15, and minus 6 is 9, but K5 has 10 edges. Right, 5 vertices, 10 around the outside, 5 around the outside, 5 around the inside. So we're going to show that K5 has one more edge than is allowed. We're also going to show that K33 has one more edge than Euler formula allows, except that value has to be brought down a little from 3 n minus 6. Right, so the way we proved that plane triangulations have 3 n minus 6 edges was to look at the bipartite graph, which has of a plane triangulation, auxiliary graph that has in one class the edges, and in the other class the faces, and we put an edge between an edge of this graph H, between an edge of D, the graph in the plane, and a face whenever this edge was on the boundary of that face. Right, and the way we arrived at 3 n minus 6 was to note, or notice, that that 2m, the number of edges of this auxiliary graph, right? M is the number of edges here. So 2m is the number of edges of H. Number of edges of H was 3 times little f, right? Because in a plane triangulation, every face has 3 edges on its boundary. So if you count these edges in 2 ways, from the left you have twice number of edges, and from the right you have 3 times number of faces. So 3f equals 2m, and then we threw in Euler's formula, and from these 2 equations, we obtained that m is exactly 3 n minus 6, right? So Euler's formula also has f in it, and you want to throw out this f and go from 3 variables to 2 variables, and you only have n and m left to give you 3 n minus 6. Now, this can be done not just for plane triangulations, but for any planar graph, and then you just get this. This. Right? Yeah, because for every face, you have a degree in H that is at least 3. Yeah, it may have only 3 edges on its boundary. All these graphs have, I don't know, more than 3 edges, vertices, right? It has at least 3 edges on its boundary. Maybe it has more, so the number of edges of H is 3f or bigger. Right. And then from this, we concluded that G has at most 3n minus 6 edges. Well, we concluded this with equality when we had equality here, and you can do that, the same thing, the same transformation with the inequality, and it flips. So this is not, I hope, well, I know it's not an intentional mistake. Let me say that much. No, it's correct, right? So, and you get that from the n minus m plus f equals 2 Euler's formula. All right? This implies that with the help of that. Okay. So in particular, if G is a planar graph, it has at most 3n minus 6 edges, and in particular, if K5 was planar, it would have at least, at most, 3 times 5 minus 6 equals 9 edges, but it has 10. So G5 is not planar. Okay. How about K33? We'll have to be a little more careful, but it's easy to be more careful. And all we need is that K33 doesn't have a triangle. So we can do the same thing here for graphs of girth at least 4. So we get the same picture. Now, we have at least 4 incident edges in this auxiliary graph H, where on the left we have the edges of our plane graph, and on the right we have the faces, and incidence means this edge is in the boundary of that face. So exactly in the same way, we get that if G is planar, and the girth is at least 4, then 2m, which is the number of edges of H, is at least 4f. And in exactly the same way, this implies, well, that the number of edges we can have is at most 2n minus 4. Right, you just do exactly the same calculation with the help of Euler's formula to get to 2n minus 4. And for K33, this is 8, but K33 has 9 edges. Okay? Questions? What have we shown? We have shown that K5, K33 cannot be planar because they have too many edges for their number of vertices, and therefore their subdivisions are also not planar. So we have shown that if G is planar, then G doesn't have a topological minor isomorphic to K5 or K33. Okay. Now let's show that this implies that. So if G doesn't have a topological minor, that's one of these two graphs, does it also not have a minor that's one of those two graphs? Well, it's easier to have a minor than a topological minor because topological minors are particular kinds of minors. Right? So we have to show something. Not having K5 and K33 even as an ordinary minor is a stronger assertion than not having them as a particular minor. Right, and so we had early on in the first chapter, when minors were introduced, this observation that for all graphs with maximum degree at most 3, and for all G, if G contains H as a minor, then G even contains H as a topological minor for H of max degree at most 3. So K33 is one of those. You get this, the ostensibly stronger assertion that K33 is a topological minor of some given G as soon as you know that it's a minor. And the way this worked was that we said, well, okay, let's look at this H. It has some branch sets. So when we looked at a model of H, one particular subgraph in IH, then if the degree of H is at most 3, then every branch set here has 3 vertices sending an edge to another branch set that we use for this. And then we said, well, it's easy then to find a branch vertex. That is, since branch sets are connected, we just find a path from one to the second, and then from this to either one of those, and maybe we hit here first. And then there's our newly found branch vertex inside the branch set. So we can turn a model of a minor, an IH, into a TH by replacing this branch set with that branch vertex. And doing the same in all the other branch sets. Okay, so what goes wrong when the max degree is bigger than 3, as it is in K5? So let me start by saying that if we have a K5 minor and we can find in there a topological K5 minor, then we'll be happy. So how would we find that? Well, we'd have 4 vertices reaching out from this branch set, from every branch set of our K5 minor. And we can connect these 4 in turn. Let me do it again in real time. So from one, we find a path to one of the others. From the next one, then, we find a path to one of the first 2. Maybe that hits here. And then from the remaining one, we find a path to all of that. And then that hits, well, there are 2 possibilities now. One is that it hits here, and the other is that it hits on one of these paths. And if in all 5 branch sets we're in the blue case, then we have our TK5. Okay, so suppose that in at least one case we don't have that, but we have this. And then we'll just declare, well, these will become branch vertices, but I want to find a K33 topological minor now. Right? You see what's happening in this implication? We're assuming that we have a K5 or K33 minor. We want a K5 or K33 topological minor. If we have this, we get it. If we have this, then either we get it or we're here. And when we're here, I want to show you ultimately that we get a TK33. But we already know it's enough to get an IK33. And that then contains a TK33. So let's get an IK33, a model of a K33 minor. And that is if we have this situation here, then we'll just create two branch sets. This is one, and this is the other. And this reaches out to two of those branch sets, and this reaches out to two of the other branch sets, to the other two branch sets. And then what we have, let me draw the minor here, the would-be K5 minor, or K33. So the other four branch sets form a K4, right? And the K5 minor. The other four branch sets, this is the fifth branch set. The other four branch sets form a K4. And now we have the fifth branch set here, and we split that into two. And this one sends edges to two of those, and this one sends edges to the other two of those. Now, why does this send edges to the right ones rather than those? Well, because this is a K4. I can flip that any way I like. Right? So I should have drawn the other later, so I should have said, okay, this sends edges to two branch sets. Let's write them on the right. This sends edges to the other two branch sets. Let's write them on the left. And then you can see a K33 minor. And that contains a K33 topological minor. Okay. So that takes us from here to there. And what remains to show now is that if we don't have a K5 or K33 minor, then we're planar. So proof of G doesn't contain K5 or K33, then G is planar. For three-connected G. I'm only going to show you the three-connected case. It's not hard to deduce from that the general case when the graph is not three-connected, there are two ways of doing that. One is topological. You can assume it has a separator of at most two vertices and then embed one side, and you can then fit an embedding of the other side into that first picture. It's a little more difficult, but not much. Basically, you can embed not only the left side, but the left side plus an edge between these two separating vertices, if that wasn't there before, because that edge is there anyway. And so that's a topological proof. And there's also a combinatorial proof, which is in the book. And yeah, that has a nice windfall that is needed later for Hadwiger's conjecture in graph theory 2, but I'm not going to show you that proof because it's a little pedestrian and just looking at cases. But it is recommended reading. Just read it once and then forget it. Okay, so let me prove that for three connected graphs. We'll do induction. That's the basic idea. We look in our arsenal of tools that we have for three connected graphs, and one of them is this nice lemma, which told us that in any three connected graph we can find an edge whose contraction yields another three connected graph. So given G, there's an edge xy in G such that when we contract it, is three connected, hence planar, by induction. Why can I use the induction hypothesis? Well, because what I'm assuming is preserved by edge contraction. What am I assuming? That we don't have a K5 or K3 minor. So if we contract something and then suddenly have such a minor, then we have that minor also in the original. We just contract one thing first and then whatever we need to contract later. Okay, so we can draw that. And we contracted this edge xy to make a contracted vertex vxy. And now embed G twiddles in the plane. So this little wave here is called a tilde. And one often says twiddles, probably because it's so much easier to pronounce than tilde. Anyway, so G tilde or twiddles goes to the plane, and here's a drawing. Now, this is one vertex that lies somewhere in the plane. If we delete it, we'll have G tilde minus one vertex, which is still two connected. This vertex that we just deleted will lie in a face of that two connected graph. And since it's two connected, that's bounded by a cycle, and let's call that C. Okay, so G twiddles dash or prime, also two words for the same thing, is G twiddles minus vxy, I think. Let me just look. No. Okay, that comes later. Don't worry. So, something will appear here. Okay, so this is just a drawing of G tilde with this one vertex, then when we delete that vertex, the point that used to be that vertex lies in some face of the resulting two-connected graph. That face is bounded by a cycle, and that's C. So C is a cycle in G tilde minus this vertex Vxy. Okay. The idea now is, or we have to, if we want to do induction, we have to now somehow use that embedding to find an embedding for G. Or we have a drawing of G in the plane. How could we use that drawing of G tilde? Well, we can draw most of G in the plane as follows. Let me show you that we can draw G minus y in the plane. And my plan is to place the vertex y, which somehow here doesn't exist. It's been merged with x. My plan is to, well, if we want to draw G minus y in the plane, then we don't have to worry about y. And we just have to embed little x. My plan is to use Vxy, the embedding of Vxy, the point in the plane that is Vxy, for x. And that's easy. I mean, we can just do that. So x has certain neighbors in G, and all these neighbors are either little y or they lie on C, because they give rise to edges between Vxy and the rest of G tilde. And the only other vertices of G tilde they can get to are vertices on C, and therefore also vertices of G. So let's call the set of neighbors of little x on C, in G, other than the vertex little y, let's call that big X. And similarly, let's do the same for y. So y has some neighbors. Maybe some are also in X, others maybe are not in X. Okay. Now, the idea for getting from the embedding of G tilde an embedding of G is by first forgetting little y and using the embedding of G minus y that comes from this embedding by letting little x use the point in the plane that Vxy occupies here, and just make it adjacent to the edges, its neighbors in G that must lie on C, and which gave rise to edges between the contracted vertex Vxy and those vertices on C in this embedding. And there's our embedding of G minus y. So that's easy. So task insert y plus incident edges in this picture. Okay? So ideally, y will have to send an edge to x, like here. So if we placed y, say here, where it's drawn here, then it couldn't send edges out as it is here. That would not make a plane graph out of G, which is our aim. But then it might have these neighbors, or might it not? No, perhaps not, because we know something about G. We know that it doesn't have a K5 or K3 minor. So the plan is to say, either we can find a nicer spot for y than here, or say that we are contradicting our assumptions because we have a K5 or K3 minor. Okay, so what would a nicer spot be? A nicer spot would be one of these segments. So for example, if we could find a segment, one of these segments here, between adjacent vertices, between blue vertices on C, that contains all the little vertices of y that are not in that contains all the neighbors of little y, then we can put y in that little pi segment, because then we'd make it adjacent to x and adjacent to all its neighbors, and we'd have an embedding of G. Well, but the neighbors of y have to lie somewhere. And let me show you that even if y has little y has a single neighbor that is not in x, in big X, but on C minus big X. Only one will do. Then we already get a contradiction. Okay? So that's case 1, y is not a subset of x. So y has an element little y prime that lies on C minus big X. And now it has another neighbor. There's another element of big Y that is not on this segment by assumption. Right? If the entire Y lies on this segment, we're done. Or at least we hope to be done. Then we put little y in there. So let's suppose that's not the case. If there's a y double dashed in C minus, no, I don't even need it outside X, just in Y minus the little segment that contains y prime, that's a big Y here. Then I'm going to find a TK33 with a contradiction. So why is that? If there's a little x, a little y double prime, say here, or maybe there, anything outside this segment, then here's my TK33. I remember the two blue vertices from big X that are the endpoints of this segment that contains little y. And then I remember this little y prime and the little y double prime that is outside this segment. And what you can see here on C, ignoring everything else on C, is 4 vertices alternating in pairs. So we'll have here a C4, it's subdivided C4, orange, red, orange, red, orange, alternating. And then we also have y somewhere in G. Now, this y sends edges to the two red vertices. And we have x that sends edges to the blue vertices. And there we have our K33. Okay? Yeah. So that's a contradiction. And therefore, we're in case 2. Y is, in fact, a subset of X. And that should be really easy now. So let's look at case 2.1. That y, that we write formally, has at most 2 vertices. Well, it can't have fewer than 2. Right, because little y was a vertex in a 3-connected graph. So that has 3 incident edges. One of them goes to X, and at least 2 go elsewhere. So then, in fact, Y has exactly 2 elements. And they're also in X. Now, the picture was here. I'll make a new picture. So we have little x. And we have little y, and x has some neighbors, big X, and y has 2 of those also as neighbors. Now, if they're adjacent in this cyclic ordering of x along C, then they lie in the same segment, albeit on the boundary, but they do lie in the same segment, and then we'd be putting y in that pi segment there. So the two neighbors of little y, the elements of big Y, are not consecutive in x. So say this and that. Right? But then again, we have a C4, subdivided C4 with two blue vertices and two green vertices alternating. And we have the same situation as here. X is adjacent to 2 and y is adjacent to the other 2. And we get a TK through 3 again. So, last case, y has at least 3 vertices. Well, then we have x, and 3 of those vertices in big X are also in big Y. And I don't care which 3. Because those 3 common neighbors of X and Y they make a triangle, a subdivided triangle. And then we have X and Y in addition, and each of them is adjacent to all of those 3, right, by original edges, and to each other. So we have a TK5. Okay. So that's the end of the proof. Any questions? Yes.
How do we know that the three vertices make a triangle? Because like y is the left one to the right one. Y is the left one to the right.
I just ignore everything else. So y, X and Y have 3 common neighbors on C. I ignore all the other edges to C. So C is a cycle going through those 3 vertices. And that is a subdivided triangle. Other questions? That's very nice. I tricked you once more. Are we really done? What could possibly not be complete? There's nothing wrong, but there's a gaping hole. Yeah?
Maybe in case 1, we see there's a y double prime.
No. So what would be the objection?
Maybe there's no y double prime.
But then they're all in the same segment. Yeah, good point. No, but you're getting there. So the point is, I said, well, if they're all in the same segment, if there exists a segment of the cycle between 2 adjacent vertices from X that contains all of big Y, then I said, okay, then we'll just put little y in that pi segment. Can you write that down mathematically? The word that pi segment. How is it defined? Right, we need this. I think I redraw here. So the situation now is that we have C and we have X, and X had various neighbors on C as well as little y, of course. And so we're now assuming that y is contained in this portion of the segment of C that has two vertices from big X at the ends, and the interior has no vertices from big X. Okay, you can now say, well, that is not really properly defined, but it really is. So you have to wheel in the definition of a cycle, and then you can prove that this exists. So, and we'd like to say, well, we want to put little y in there. So let's sort of give this a tentative name. That is little fi, or maybe I'll make it red. This is my intended pi segment. And that's a cycle. It really is a cycle. So this is a path, and X is not on that path. So this is a cycle. Let's call that Ci. And this vertex here is little xi, which is in big X. And this is little, I don't know, xi plus 1, which is also in big X. So this cycle Ci is defined, and I would like to point to this face of this little cycle and call that Fi. And the trouble is, how do I write down the definition of Fi? Rather than saying that one. So Ci has two faces, right? This one and that one. I have to define it. Well, it's not that hard. So we can you come up with a definition, a formal definition of Fi? That's not the hard part. Well, there's no hard part, but okay, so let me say it's the face of Ci that doesn't contain, let me call this segment here Pi, right? This segment here, that doesn't contain C minus Pi. So C minus Pi is this set of points. That set of points lies in one face of Fi. Why? Because all these points are equivalent. You can get from any one of them to any other by a polygonal arc that doesn't hit Ci. Okay, so they all lie in one face of Fi, of Ci, and I'm decreeing that Fi shall please be the other face. And from Jordan, we know that there are two faces. Okay, so we have a definition of Fi, at least. Next, I want to show that Fi is a subset of F. Right, so F was sort of, if I'm allowed to point, I would say this. If I'm not allowed to point, I'll have to remember the definition of F. What was the definition of F? The definition of F was the face of G tilde minus the contracted vertex that contained the point of that contracted vertex. So once more, we had G tilde, which was G with the edge xy contracted to a vertex vxy. That went in the plane. We had a plane drawing of that. And vxy was somewhere. And we said, now, in that drawing, if we delete vxy, the graph is still two connected. So every face is bounded by a cycle. And the little vxy, that is a point now in the plane minus the graph G tilde minus vxy. And that therefore lies in some face, and that face is bounded by a cycle, and that cycle gets the name of C. Okay. But we had a lemma early on which said that every face of a plane graph is a face also of its own boundary. So its boundary is a subgraph of that graph. That was a long proof. Boundary is never half an edge, that proof, remember? So the boundary of any face, such as F now, of the appropriate graph, is a subgraph of that graph, and then it's a boundary also of that subgraph. So F is a face also of that subgraph. So F is also a face of C. Now, Fi doesn't meet C, as Fi intersection C is empty. That's by definition of Fi. Right? Fi doesn't contain a point from Pi, because Pi is on the cycle Ci, of which Fi is a face. So Fi certainly doesn't contain a point from Pi, and it doesn't contain another point from C by definition of Fi. So we know that it's contained in a face, let's call it F prime for the time being, of C. Right? Fi doesn't meet C, therefore it lies in a face of C. But we can say that this particular face of C is this F. Why? Because Fi meets F. And why is that so? Because pick a neighborhood of the point where Vxy was drawn that is so small that it doesn't meet C. And that is certainly possible. But every neighborhood of this point, because this point lies on Ci, little x lies on, this is now x, right? X lies on Ci, also has a point in Fi. So this little point here is both an Fi and an F. So this face of C that Fi lies in can only be F. It can't be the other face of C. Right. So we have now shown this. So we have defined Fi. We have shown that it's a subset of F. And we want to show that we can put little y in Fi and join it up to its neighbors. But this Fi here, that doesn't meet any of the other stuff that lies in F. What lies in F? Only the edges from, so in the graph G minus y that we have embedded, right, we've appropriated this vertex Vxy, the contracted vertex, and called it x, forgotten about the edges that y sent anywhere here for the time being. So we have this embedding of G minus y. And we have this face F of C. And also of G minus y minus x. That contains this little point x. And of this graph here, the only other stuff it contains are edges from little x to big X. But none of those have a point in Fi. Why? Because if they did, they couldn't meet these two edges, because edges are disjoint, except in their end vertices. So if any of these edges had a point in there, it couldn't get out unless having its point of C in here, but that it doesn't do by choice of little xi and little xi plus 1. So all these other blue edges here from x to little x to c lie properly outside, thoroughly outside Fi. So Fi, I can put that here. Hence, Fi lies in plane minus G minus y. I mean, in the embedding here. And now we can really pick any point from Fi, put our little y in there. And join it to its neighbors. And now we really are done. So what are its neighbors? Little x. We can do that from Fi. Little x is on the boundary of Fi. Yeah, that was one of these early topological thingies which I meant to say and then ended up not saying, that every point on the boundary of a face is accessible by an arc from that face. But that's easy because we have polygonal arcs. It's also true in general, but for polygonal arcs, it's easy. You just choose a very, very small little disk around it where this boundary consists only of either one edge, one straight segment or two, and then you can find such an arc. So little y can send a plane edge to x, and it can send plane edges to all its other neighbors. And that, of course, this too is, you could nail me down and say, well, how exactly do that, please? How do you do that, please? And yes, you have to join it one at a time. So you join it to x, you can prove such a polygonal arc exists, then you want to join it to this, say, okay, let's draw a path from here to y, and oh shit, it hits here. And I say, yeah, just stop a little before and then follow that, and so on. That's fiddly, but easy. And now, I claim we're really done. Are there any questions? No, and I think that's all I want to say. Oh no, there's one more remark. Yeah, so please do just once read the deduction of the general case for graphs that are not three-connected from the three-connected case. And that deduction has a little corollary of its own, and that is that any maximally planar graph with at least 4 vertices is in fact three-connected. That's sort of not so trivial by itself. So if you have a two separator, somehow you want to say, oh yeah, then I can draw another edge. Okay, so just memorize that fact. It's a useful fact, right? So maximally planar graphs are, in fact, three-connected, unless, I don't know, they have only 3 vertices, which is why this really is the most important case. Okay, then thank you very much.